Buenos dias, amigos. Welcome to day 3 of e-learning. First day, you guys took a little test on energy that we were discussing before we left. Yesterday, you learned what momentum was. So momentum, whose symbol is P, is equal to your mass times your velocity. And you did some various problems on that in your homework yesterday. Today, we're going to get into the second term, impulse, which is probably a much less familiar term than momentum. So let's jump right in. First of all, what is impulse? Impulse is a quantity that describes how a net force affects an object. The symbol for impulse, uppercase J. Interesting choice. So let's take a look at this. We've got Newton's second law. Net force equals mass times acceleration. If you were to take that acceleration and expand it to be a change in velocity over time, and then take that time on the denominator and bring it over to the other side, now you've got net force times T equals m delta V. This equation, believe it or not, that we just derived has a name. It's called the impulse momentum theorem. You learned yesterday that m delta V is called the change in momentum of an object, because mv is momentum, so change would be m delta v. So this right-hand side is our change in momentum, and it's the impulse momentum theorem, so the left-hand side here is called the impulse. One little detail to add here is that this force we've been talking about, we're going to call it our average force, so we're going to put a little hat on top of the symbol there. Doesn't change anything, but here we have our impulse momentum theorem. And basically what it says is that a force that's acting over a certain amount of time on an object is going to change that object's momentum in the form of its velocity, speeding up, slowing down, so etc. It's always a good idea to double check the units to make sure that an equation you derived checks out. So force we know is measured in newtons, time would be measured in seconds, and change of momentum here, mass would be in kilograms, and change of velocity would be in meters per second. So first inspection here, it doesn't look like these two sides have the same units, but if you remember what a newton is, a newton is a kilogram meter per second squared. So I'm going to plug that in for n. So I've got kilogram meter times seconds all over seconds squared, and then I've got kilogram meters over seconds on the right hand side. These seconds, one of them cancels on the left, so you'd end up with kilogram meters over seconds and kilogram meters over seconds. So units check out. Now let's take a look at a graph to kind of show this relationship. What we're going to do is make a force, net force versus time graph, and we're going to do this for a situation where a person is standing still and one of their friends, or so-called friends, throws a soccer ball at their head from point-blank range. And we're going to graph the net force on the person's head due to the soccer ball. Now we do have a video to go along with this. Add a little bit here.
Alright, well, this is my
chit chat.
favorite part of the challenge. I don't know yours.
Okay, slow motion. Boom. Watching that again here. Kaboom. Now, the force from the ball in the head is not consistent. When the ball first touches his face, the force is low. but it increases up to a maximum amount. Then it starts to rebound back away from his face, and slowly it eventually is no longer touching his face here at the end. This force curve is very common in terms of collisions, so you could look up this kind of a curve for a car running into a barrier, any kind of collision where two things run into each other. You usually get a bell curve kind of shape. Now, how does this graph fit with this impulse momentum theorem? Well, the area between this graph line and the x-axis represents the impulse, in this case, the person's face. If you're in calculus, I know that we have a few calculus people, impulse is really just the integral of the force with respect to time. So in other words, the area of a force-time graph. We have really nice computers and software on the computers like Capstone that can find the area of these graphs really well. Since this shape is not super easy for us to integrate or find the area of by hand, one neat trick is that if you were to find the average force on the face, so somewhere right around the middle of the bell curve, and just make a rectangle going to that time when the ball is no longer touching. And if you were to find the area of this rectangle, and I'm shading here in orange, that would be approximately the same as the area of the bell curve. So that's a good way to approximate the impulse on an object, would be to go where the average force is and multiply it by time, which is exactly what impulse is. It's average force multiplied by time. It's the area of that rectangle that we just made. Now let's make some real-world connections. Let's imagine that you've got a car. And they're driving along. And there's a barrier up here. And for whatever reason, the car is going to run into this barrier and come to a stop. The driver of this car, in scenario 1, in the first scenario here, not wearing their seatbelt, and let's say the car doesn't have an airbag. Okay, this driver, when the car hits the wall, is going to come to a stop very abruptly. So if we were to make a force versus time graph for the force acting on this person by the dashboard of the car to come to a stop, you're going to get a really tall graph. It's going to be very skinny. Okay, this force is going to be really, really high because the time period that this crash takes place over is going to be a really short time. Now, redo the situation. Same person, same car, same speed they're driving at. But this time the driver runs into an airbag or is wearing their seatbelt. And what the airbag and the seatbelt do is they stretch out the time period over which the person stops. So we'd end up with a graph that's a lot less tall, but wider. Not a great bell curve there, but you get the point. The average force on the first driver, we'll do that in red, somewhere up here. In green, the average force somewhere down here. Okay, right in the middle of the green curve versus right in the middle of the red curve. What's important to remember about these two curves is that we're talking impulse momentum here. So Ft equals m delta v. The person's mass isn't going to change in the problem from start to finish. So m doesn't change. Delta v is just final velocity minus initial velocity, which again is the same. The initial velocity of the cars was the same. Their final velocities are both 0. So nothing changes on the right-hand side of the equation. So that means the only things that can change from scenario A and B are the left variables, force and time. The bigger this time variable becomes, the smaller the average force becomes in turn, because the m delta v never changes. The product of F times t can't change. Bigger t, smaller average force. Smaller t, bigger average force. And that change, that difference in force from the red to the green graph can be the difference between life and death, or a major injury versus a minor one. And there are lots of situations in life where this the relationship between force and time for a collision is very important. For example, when you jump up and down, when you land, you don't just land straight-legged. What do? You bend your knees. So by bending your knees, you slow yourself down over a longer period of time. Time is bigger, the average force on your legs is much less. And you can think of all kinds of sports equipment, safety features in cars. These are all taking advantage of the impulse momentum theorem. All right, let's get on to our last example here. If a 5 kilogram object was moving at 2 meters per second at time 0 seconds, how fast was it moving at 8 seconds? So I've got a force time graph here showing that this object's getting pushed around by different forces. We don't know what those forces are, but it doesn't matter. We know our initial velocity is 2, and 8 seconds later we want to know how fast it's going based on this force time graph. So again, the area between our graphed line and the x-axis is going to represent the impulse. So I'm going to break this up into some geometric shapes and find their areas and add them up. First we've got 20 by 4, so that's 80. Then we've got 1 by 20 divided by 2 because it's a triangle, so that's only 10. Here, same thing, but below the x-axis, 1 times 20, negative 20, and then divided by 2 would be negative 10. And then 2 by negative 20 is negative 40. So adding up our area, the area here represents the impulse. That would be 80 plus 10 minus 10 minus 40 gives us an impulse of 40. And we know that impulse equals let's just go change in momentum to start. So if we have 40 equals m delta v, and we knew that our mass from this problem was 5. Change in velocity is final velocity minus initial, which was 2. So I can divide by 5, I get 8 equals vf minus 2. Add 2, and our final velocity of our object is 10 meters